start our examples for 6.3. We'll start out real easy. It's not too tricky to figure out whether something is binomial or not. We got to check those bins. So for A, if you roll a pair of die 10 times and let x be the number of sixes, okay, is that random variable x? Is it binary? Is it either 6 or not? Yes, right? So is it binary? Yes. Is each trial independent of the next? Yes. Are there a fixed number of trials? Absolutely, you're doing it 10 times. And is the probability of success the same for each trial? Yeah, right? And that checks out too, right? It is 1 in 6 every single time. All right, let's look at B. You shoot a basketball 20 times from various distances on the court. That Y equal the number of shots made. Well, is it binary? Yes, right? You either make the shot or you don't. Is each probability, does it matter if you make one shot? Does it affect the probability of you making the next shot? It does not, right? Are there a fixed number of trials? Yes. Is the probability of success the same for each trial? And that's a no, right? Because if he's standing right up on the basket, it probably has a better probability of making it than, or he or she probably has a better probability of making it than if you are somewhere far away. So B is not a binomial setting. Doesn't have a binomial. The random variable y does not have a binomial distribution. You could say as well. C. We observe the next 100 cars that go by and let C equal colors. Is it binary? No. So right away we're done. Because it could be, C could be blue, green, aqua, aquamarine, aqua tan. No? Is that not a color? Aqua tan?
I'm going to search that.
I just went tan. That just sounds disgusting. I'm sorry. But like, that's like
I feel like that could be like, you know, like there's like that clear ocean and you see like the sand. I feel like it's like that.
That is the color of aqua tan. I don't know. Who knows? Alright. So we got to that. There we go. In many games involving dice, doubles is desirable, aka Monopoly. Oh my goodness. That was weird. Okay. Alright. Yes. Rolling doubles means the outcomes of the two dice are the same, such as 1 and 1 or 5 and 5. The probability of rolling doubles when rolling two dice is 6 out of 36. We could have figured that out. Come on. Which is the same thing as 1, 6. So if the random variable x is the number of doubles in 4 rolls of 2 dice, then x is binomial with n equal to 4 and p equal to 1, 6. What is the probability that x equals 0? That is, what is the probability that all 4 rolls are not doubles? Now, you could make this real hard. But we're just going to go, well, first of all, I guess we should plug it into our binomial formula. Just to be super thorough. You don't have to do this, but it's good to be able to do it. So I'm going to plug some stuff into our binomial probability formula here. Just to get us used to seeing what goes where, and then we'll use our calculator to actually calculate it. All right. So the probability that x is equal to 0 is going to be n k p to the k 1 minus p to the n minus k. I almost think I got that right. I actually did get it right. Because I went to college. No, when I studied this stuff in college, you had to do it like this. Like, it was absolutely required that you showed this and then went through the steps. They did not want you to use it. Alright, so we can actually calculate this. I mean, the other option is to go binomial PDF. Yes. 4 over 0. That's essentially 4 choose 0. No, it does not. It is the binomial coefficient, which is n factorial divided by k factorial times n minus k factorial, I think. I don't think that's right, and it's not on your formula sheet.
It's okay, I was just confused.
It's the binomial coefficient. So
It's just there.
you could calculate that. Actually, there is a combination button on your calculator, right? This essentially says 4, 0, should be 1. And what this does is it calculates that binomial coefficient with n equals. So that's what's going on, and it's just doing that formula that I showed you guys. It's just running through there. So, all right. While we have this open, let's go ahead and calculate it using our calculator. So we're going to hit probability. We're going to go to distributions, and we're going to go to binomial p dizzle f dizzle.
P dizzle f dizzle?
Yeah, PDF. So I was awakening my inner Steve Jobs. Okay, the number of trials is going to be 4. Probability of success, I can actually just put 1/6 in there. And my x value I'm looking for is 0. Is everybody there?
No.
Yes. Yes.
Wait, where did you get that little back?
Yeah. Does that have sugar in it?
What you're gonna say was
I hit OK.
Those cookies are really good.
okay.
And there it is. So our probability is going to be approximately 0.482.
Wow, I did it. And we just put the calculations like
Exactly. So you can put binom PDF, right? I did it right. 4, 1, 6, 0. approximately. Well, that's what you'll put in. Since we have this here, I would prefer to put 24. It's the same, right? Either of those are acceptable responses. You can use either.
How do I charge it?
Just grab one of these here. And then,
Well, I'll just use this.
one that Josh isn't using. Let's see. These two have fresh batteries right here. Okay. Done. Boom. Hey, same one. Suppose the game player rolls a dice 4 times, hoping to roll doubles. If you did that in Monopoly, you would be in jail. Find the probability that the player gets doubles twice in 4 attempts. What are we being asked for in A? We're being asked for the probability that X is 2. Right? And we know that N, our number of trials, is 4. And our probability is 1/6. So I'm going to go ahead and show that we're going to plug in binom PDF, where N is 4. It goes N, P, X. Okie dokie. Let's go to our calculator. Hey, cool thing about this is I could just go up. Whoa, I skipped one. Just copy this bad boy and change X to 2. And we get approximately 0.116. We're gonna get there, I believe. Here we go. Right now, in B. They're on top of it, following order. Would we be surprised if he gets doubles more than twice in 4 attempts? So, in other words, we're being asked, what is the probability that X is more than twice, so greater than 2? Right? Which is the probability that X is equal to 3, plus the probability that X is equal to 4, right? Either one of those counts, right? You get it on the 3rd try. Sorry, that you get, my bad. You get 3 doubles or you get 4 doubles. Sorry, I switched over to a different probability distribution. Cool thing is I don't have to do those separately. I have the binomial CDF function. So we'll get some approximate value. And I'm going to put in here binom CDF, and I'm going to put my... It said more than twice in 4 attempts. Oh, sorry. Yeah, more than twice, 3, 4.
So the number of trials is still 4.
Huh?
Probabilities is still lower than?
Okay, so if I wanted to look at the event that I get 3 doubles, I roll it 4 times and I get 3 doubles, right? That's going to be greater than 2, right? And then the probability that I roll it 4 times and get 4 doubles, that's also greater than 2. Right? So either one of these events counts as a success for the probability that there are more than 2 doubles. You know what I'm saying? So then my lower bound is going to be 3. So this is the way that's going to work. And you'll see it on your calculator. We're just going to put it in there first. See? So you're going to put lower bound comma, upper bound,
I'm dressing this sweater like
comma, n, whoops. Now I'm doubting myself. Comma, n, comma, p. Ooh, I hope that's right. For some reason, I'm feeling a twinge of doubt. So let's put it in the calculator. The calculator will arrange this for us. So here we go. We will go to menu, probability, distributions. I want binomial CDF. And then my number of trials is going to be 4. Probability is 1/6. I have a feeling that I put it wrong in the previous one, but we'll see. 3. Upper bound is 4.
Oh, 3 to 4. So if it was asking, like, if we had, like, 6 trials, so then it would be 3, and then upper bound would be 6.
Yep. You got it. Alright, we will head over. Nope, I did it wrong.
Try again.
It's NP lower upper. Sorry about that. NP lower upper. P lower. Sorry about that. You guys are so lucky you have your Inspires, because if you had one of these old guys, so the first time I taught AP statistics, I taught it with a TI-83 plus. And you had to memorize the order of each of these. And they're different. You notice that for a normal distribution, it's lower, upper, mean, standard deviation, right? This one is NP, lower, upper, pretty easy to get confused. So this TI Inspire, I think, is probably increased AP stat grade across the board for classes at home. All right, so it's approximately 0.016. I feel obligated for some reason to put them both there. So I do. I don't know why. There'll be no mistake as to what you believe the answer is. If you put it twice. Huh?
Yeah, I have them all over the list. I don't know. Like, I remember right here.
All right.
Yeah.
So, we're wondering if people have a preference for the last thing they taste. Researchers gave 22 students 5 Hershey's Kisses. Haha, the last kiss. They're so clever.
Get it?
The last kiss. Alright, so they've got different flavors of kisses. They're told how many kisses they would be tasting. But when the 5th and final kiss was presented, participants were told that it was their last one.
Oh.
Of the 22 students, 14 of them gave the final kiss the highest rating. We gotta assume that there's not a special preference. In other words, that the probability is the same for each trial. And the probability for the last kiss is 0.20. What is the probability that exactly 5 of the 25 participants would prefer the last kiss that they try? Is it binary? Yes. Each trial is independent? Yes. Set number of trials? Yes, there are 22 participants. Probability of success is the same? Yes. Does really feel like I have to go through that as a formality? Yes.
How do you know it's binary? I know that's like
It's either yes or no.
But like, yeah, how do you know yes or no?
It's either they preferred it or they did not. So, oh, you weren't here for the first example. Alright, so probability of exactly 5. So that's a probability that x is equal to 5. We're going to, since it says just equals, we'll use PDF, right? And as a rule of thumb, right, if you're looking at the probability that x is greater than or less than some value, you will use binomial CDF. If you're looking at the probability that x is exactly equal to some value, you will use binomial PDF. So that's the case right here. So binom, P dizzle, F izzle, NP X, N, P, X. I'm sure it's not necessary to put both, to put the answers under both. For some reason, I really want to do it. So I can just go up. N is 22. P is 22. X is 5. No syntax. Here we go. Probability is approximately 0.19 when we round to the thousandths place. This stuff is not bad, right? Not too bad. How about I just have to do it. I can't like not do it for some reason. Makes me feel weird. All right. What is the probability that 14 or more, huh? Yeah. Oh, really? No.
At least you say it.
No, I can think of way weirder things than that. That make me feel way more uncomfortable. Okay, x is more than 14 or more. 14 or more of the, there we go, that's what that looks like, right? And now I wrote that was, probability x equals 14, probability x equals 15, 16, 17, so on, all the way up to 22. If I wrote all of that, I would write a lot of stuff. It's not really necessary. What I need to do is binom CDF, and then I'm just going to get this value right off the key so that I don't screw it up again. So let's go ahead and do that. Let's go menu, probability, distributions, binomial CDF. My number of trials is 22. My probability of success is 0.2. My lower bound is 14 because it includes 14. And my upper bound is 22. Ooh, wow. That is a very, very, very low probability. There's 4 zeros. So that is and this is N, P, lower, it's 14 or more. So that's not very likely. Okay. All right. Moving on. If X is the number of, ooh, hey,
I mean, like, I can't really feel
Maybe we'll have it. Okay.
it.
If x is the number of doubles in 4 attempts, back to our doubles thing. X follows a binomial distribution with n equals 4 and p equals 1, 6. By the way, if the problem says it follows a binomial distribution, you don't need to check things anymore. It's already been said, hey, it's binomial, so you don't need to check.
Cool.
So we don't have to check. It says here is the probability distribution and a histogram of the probability distribution. You know what? We're going to make it ourselves. So we're going to use our handy dandy calculator. We are going to have to make a document if we want to make a histogram and construct this probability distribution. We can do this with any probability distribution. We've done it before, but you can do it pretty quickly with a binomial distribution because you have a function that works it all out for you. So we're going to add a list in spreadsheet. We're going to name our first column x, as in our random variable x. We're going to name this px, like as in the probability of x occurring. Over here, how many trials were there? I forget. 4 attempts. So that means that my possible values of my random variable x are 0 through 4, right? The probability that I get, or that's the event of 0 doubles, 1 double, 2 doubles, 3 doubles, or 4 doubles, right? Those are all of our possible values that our random variable x can have. Over yonder, I want the probability of 0. I could go in and do binomial PDF tons and tons of times, right? But I don't have to do that. I can actually get my calculator to do it. I can say equals, and then go to menu. We'll go to statistics. Choose distributions. Are we okay?
Yeah.
And then we'll go to binomial PDF. My number of trials is 4. Probability of success is 1/6. And my x value now, I'm going to put in a variable. I'm going to put in that variable x that I defined as my random variable in column A. And then I'll take all of column B. I just had a Aladdin moment. Yeah. Have some of column A, have all of column B. Your calculator doesn't understand. It's saying, hey, this x, are you talking about the column x that's way down over here to the right? Or are you talking about a variable? And you're like, no, I assigned that a variable. And so now you can go ahead and there is your probability distribution. I feel like I can actually cheat.
Wow, was Bernie cheating?
It's not cheating, it's just being efficient.
Well, yeah, next time I do a test, which is never, I'm just gonna be like,
Oh yeah, I'm not cheating, I'm just
being
cheating.
efficient.
Come on now, let's go. Alright? So then if I wanted to draw this out, I'll put it in a box. This is x. This is the probability of x. Yeah, I don't know. I guess it keeps going. I'm not sure. That's a pretty darn good question. Is it 00717? Oh, it's in scientific notation. This should be times 10 to that power. That's what that is. So it's not that great. I guess I should have changed. Okay, let's graph it. So normally you would write that out in a nice way. I just don't have my calculator separate from what I'm writing on, so it's very difficult to do. Or just tedious. So I'll hit doc. I'm going to insert data and statistics because I want to make a graph. And I'm going to go ahead and let my calculator do it. So I enter this data and statistics page. I'm going to give this the random variable x. And then you would think that you would come up here and let your y-axis be px. Don't do it, because then you're saying that you have some sort of a bivariate relationship between x and p of x, right? But that's not what you really want. You just want a relative frequency, right, of p of x. So in order to get a relative frequency, you will hit menu, properties, and then you're going to add a y summary list. Okay, so we're going to do that. We will call that y summary list px. And now
Wow.
and that's what a binomial distribution should look like, right? It's going to be fairly common to have lower values of x, and super uncommon to have higher values of x.
So like, where do you get super high value of x?
Of what? Of like that. The probability of a super high value of x is also super high.
Yeah.
It doesn't make sense for a binomial. They don't behave that way. It would be weird. Then it was probably not a binomial distribution. I'm not going to draw the graph. There it is. Let's move on. All right, makers of Coca-Cola. Okay. Claim that its taste is innocent. Ew. No, that's not true.
What's not true?
That Diet Coke is the flavor of Diet Coke is indistinguishable from regular Coke.
That's not true.
Started working at Firehouse, and they have one of the machines that has like a screen that has like 76 different flavors. And that's
Cool guy stuff.
No, it's not.
It's kind of gross.
Not. I don't like it either. So, Emily, she made some small samples of each soda, had volunteers taste, and try to identify which was the Diet Cola and which was the regular cola. Overall, 23 of the 30 subjects made the correct identification. If we assume the volunteers really couldn't tell the difference, then each one was guessing with a 1/2 chance of being correct. So let's let X be the number of volunteers who correctly identify the colas. So, why is X binomial? Because it's either they got it right or not, right? Either they said it was, either they guessed the correct one or not. Furthermore, the fact that one person guesses it correct is definitely not going to affect the probability that another person guesses it correct. There is a set number of trials. There are 30 trials, and the probability of success is the same for each trial. It's 1/2. So that is if they really couldn't tell the difference, right? It's going to change if you put into consideration the fact that they probably can. A is done. We'll find the mean and the standard deviation. Ooh, something different.
You just look dead in the eyes.
All right. B. So this is on your handy dandy formula sheet. Right. It's weird. There we go. There's any standard deviation. And it tells you the binomial distribution. Yep. Don't worry about that mu sub p hat and that sigma sub p hat. Those are for population. So we're not there yet. We haven't really talked about population proportions. So let's go ahead. So, first of all, mu sub x is going to be just p times n or np. I'm going to do it in the right order. So n times p, which turns out to be 30, times 0.5, which is 15. So if you were to do this, so what you would expect for around 15 of them to guess it correct. Our sigma sub x, our standard deviation, is the square root of n times p, 1 minus p. So n times 1 minus p, which is the complement. It's kind of interesting. It's the square root of n times the probability that it doesn't occur times p as well, isn't it? Yeah, minus the p. All right. It's n times p times 1 minus p. All right. So that is the square root of 30 times 0.5 times 1 minus 0.5, which turns out to be approximately, let's go ahead and put that into our handy dandy calculator. I'll get my calculator button out. Boom, square root of n times p times 1 minus p, which is just the same as p. Right? And we get approximately 2.739. Hey, real quick, we haven't been doing any geometric stuff, and I just want to get an example in there. Kind of interesting. What's the probability that the first guess occurs on the 5th try? Okay. Probability that the first guess occurs on the 5th trial. So, yep. So that's going to be, so I'm going to put D here.
Wait, the correct first guess?
Yeah, they get it correct. First guess is correct. On the 5th try. So that's going to be geometric. And we'll be looking at the probability that x is equal to 5. So that's going to be, forget what your calculator spits out, honestly. Let's go ahead and calculate it. So we're going to menu. Probability, always just going to the same place, right? And now we're going to find geometric PDF. And our probability of success is 0.5.
Probability of what?
Success.
Sorry.
Alright,
I thought you said something else.
I almost.
You almost did.
You just stated.
5. We're going with x equals 5. So that probability is approximately 0.03. You know. With, I believe it's just nx. No, px. Px. So that's how you do that. Let's take this thing home. Of the 30 volunteers, 23 made correct identifications. Does this give convincing evidence that the volunteers can taste the difference between diet and regular colas? And now we're starting to get into real what statistics is for, right? So, is the probability that x equals 23 unusual? And that's what we want to know. Is this an unusual probability? And we're going to get a little foreshadowing to make sure I put the right number. If that probability so I should say our cutoff is 0.05. I actually had a student ask me in the last class, well, what's unusual? I was like, well, if there was a less than a 5% chance of that occurring, you would say that's very unusual. Or unusual enough to be significantly unusual. So,
Anything above 50%?
0.05. So, anything above 5% is not that unusual. Not unusual enough. So you could say that if there was a 0.05 probability of something happening, you would say that's unusual enough that it probably didn't happen despite. There's some other factor other than just sheer chance. Line PDF NPX N P X. Let's see what that is. You've almost. There were 30 trials, right?
Wait. You did. You just did it.
And we're looking at 23.
You did. You clicked it in there. Oh, I did.
Alright, so that is very, very unlikely to happen, right? Which gives you evidence that people can tell the difference. You see where we're going with this? Where we're going to actually start, so problems are going to start to get like that, where we're going to have some situation, we'll calculate a probability of that actually occurring.
But it's unlikely, so it's or that you can know.
It is very unlikely that 23 of them would get it right, right? Which means that there's evidence that they probably can tell the difference.
Can?
Yes. So if the probability of that occurring was super high, right? You would say, well, I mean, maybe it happened by chance. Know what I mean? Okay.
If it was unlikely for that to happen, then wouldn't it be that it was unlikely that they would actually be able to test? So
Okay, so let's add a phrase to that. It's unlikely for it to happen by chance.
yeah, so something was
So in other words, there was some other influence other than just chance, meaning that and that influence is probably taken place. Yeah? We're going to do that lots and lots and lots. So it's going to sink in. So 0.002 approximately. All right, cool. So it says almost everyone has one. A drawer that holds miscellaneous batteries of all sizes. You got a drawer. In that drawer is like some tape, scissors, random batteries, a thumb drive, calculators. There's a ruler in there, some sticky notes, random junk, maybe a nail, some thumbtacks floating around. What else is in there?
Birthday candles.
Birthday candles, yeah. What's in our junk drawer? We have one. It's not a junk drawer. People call it the junk drawer, but. Huh? You have what in there? Random cords. In this case, their junk drawer has miscellaneous batteries of all sizes. Suppose that your drawer contains 8 AAA batteries, but only 6 of them are good. Throw away these batteries, people! Alright, you need to choose 4 for your graphing calculator. If you randomly select 4 batteries, what is the probability that all 4 of them will work? So, the first thing we need to do, if we're going to use our binomial distribution in order to calculate this probability is go through bins. So B, is it binomial? It's binary, rather. Yeah, either the battery works or it doesn't, right? So let's check. Is each trial independent? If you are going to take the battery out, test it, and then put it back into the jumbled up drawer, then yes. But why would you do that? Then you just keep picking the same battery over and over again, right? So this is a fail. So then we would have to use some other type of probability. The whole point of this question is to show that you really need to be careful. They're not always going to check, okay? Be careful before you go ahead and assume it's fundamental. I'm not going to calculate this proper probability going back to chapter 5 because we got stuff to do. So just wanted to show. Yeah, you would have to just like figure it out. Yeah, use probability rules on this one. All right. Monopoly. Hey, one way to get out of jail is to roll doubles, but only fools do that. Pay your $50. Get out of jail free.
Get out of jail free card? What?
Or no, not get out of jail free. You pay $50. You pay your $50 and get out of jail on the next turn.
That sucks. Takashi wasn't able to do that. Well, he wanted. He put 1.7 million. And still didn't get it.
Okay. Current events. Okay.
It's rough like
Suppose this was the only way a player could get out of jail. The random variable of interest is y, the number of attempts that it takes to roll doubles one time. Each attempt is one trial of a chance process. Knowing the outcome of previous rolls does not tell us anything about future rolls. On each roll, probability of success is 1 out of 6. But this is a geometric setting because y counts the number of attempts it takes to get doubles. It is a geometric random variable with the parameter p equals 1/6.
Why'd you say it?
Because I didn't hurry.
It's like you were trying to go fast, but it felt like you were stopping.
Before I stumbled over my words, I did.
Yeah.
And now I'm just going to talk really fast.
Okay.
Fair enough. So, hey, find the probability that it takes 3 turns to roll doubles. In other words, you roll doubles on the 3rd turn. Okay? So we want to know the probability that x equals to 3. We're going to use geometric, so we're going to go
Okay, so then.
And let's look at that on our handy dandy calculator.
If I can see myself now.
So we have to take a different approach to this problem. There is no upper bound of infinity, right? For this, it won't work. If you try to put your upper bound as infinity in here, it's not going to like it. So instead, we'll take the complement, right? We'll find the probability that y is less than or equal to 3. We'll subtract from 1. And that will give us the probability that y is strictly greater than 3. So we'll go to our handy dandy calculator. Our lower bound will be 1. It can't be 0 because that's weird to say that we get our first success on the 0th trial. That would be weird, right? So with a binomial distribution, you could have your lower bound be 0, right? Because that would be the probability of 0 successes. But it doesn't make sense to have a lower bound of 0 for a geometric distribution. Our upper bound is going to be 3 because we can count 3 on this one. We hit enter, and it is P lower upper. P lower upper. So, P lower upper. And we got that this is 1 minus 0. Yes. Oh, 1 over 6. I don't know why. Thank you. For some reason, I decided to. I guess I have an eraser. That would be a better way to do that. See how my teachers love me so much because I would use my eraser. Maybe like it. I can't reach it. Wrong one? Approximately 0.421. So then I can go to my handy dandy calculator. That is approximately 0.579. Pretty good chance that you're not going to get out of jail by rolling the dice. So what do? You pay your $50 and you play the game, okay? Just smart. You gotta play smart Monopoly. When the game is at the final throes of everything, where do you want to be? In jail. That's when it's going to be time to roll, right? Because you can collect money in jail, but you can't lose money in jail.
Well, must be research, you know?
I'm talking about Monopoly.
Yeah, I know.
All right. That is that.
Sure.
Just saying.